So good morning. We look at the problem of reducing the order of a homogeneous linear differential equation, provided we know somehow one solution, or more generally, suppose you know k solutions where k is less than the order of the differential equation, we can reduce the order of the equation or the problem, reduce the problem to solving a n minus kth order differential equation to find the remaining linearly independent vectors which span the out space. Okay, so that's the problem. So let me just write down the problem. Given an nth order homogeneous linear ODE, is it possible to reduce the problem to solving a lower order equation provided exploiting the knowledge of linearly independent solutions. Now, this we have seen in nth order systems of first order equations or n simultaneous first order systems of equations which are homogeneous. In that case, we have already seen that if you know one solution, you can reduce the order of the equation, so that finding out a basis for the solution space becomes finding out solving a lower order or finding a set of fundamental solutions of a lower order equation. The same thing how it looks in the case of higher order linear homogeneous differential equations in one unknown. This is the question that we are taking, a very special case of that. Okay, so we have the following theorem. Let eta t be a non-trivial solution of the nth order homogeneous linear differential equation defined by the nth derivative plus equal to 0, where pi's are assumed to be continuous on some interval p2 and not equal to 0 for every or on any subinterval where eta t does not vanish. Then the transformation x yt reduces the equation 1 to an equation of order n minus 1 in z is equal to y derivative. Now it's quite simple to prove. I mean, it's not no complication at all. What you do is, the proof is very simple. X equal to eta y eta. Then we have the following. Then we have eta y equal to lower order terms. And that's quite easy to verify. Okay. Now divide by eta. Eta. See, here we use we have y satisfying equation, something like sigma this is equal to 0. Where of course Q's are Qi's are determined in terms of Vj's, eta, now Qj's are Qi's are continuous solutions. Now what we observe is that now we see that equations equivalent implies and y identically equal to 1, that is the one corresponding to x equal to eta, is a solution of Q. And what does that mean? That means the following. Implies, because this corresponds to therefore what happens, y identically equal to 1 is a solution of this, implies, so you just set y identically equal to 1, the last term we get q n t is identically equal to 0. Therefore 1 to n minus 1 QIT equal to 0, which allows us to just replace or substitute y derivative equal to z in this equation. Substitute y derivative equal to z. Then the equation 3 reduces to so this is the reduced equation. This homogeneous equation n minus 1 and any fundamental set of solutions provide us with a fundamental set of solutions of equation. Assume linearly independent set of solutions of minus 1. Linearly independent set of solutions of 4, then yi equal to integral determines yn minus 1. Now, the corresponding xi's are x1, eta 1 y1, eta y1, eta y2, etc. eta yn minus 1. Now the first thing that you observe is that these are linearly independent. How do you do that? Take a linear combination of this and set that equal to 0. Then you see that eta is now nowhere vanishing, therefore it says c1 y1 plus c2 y2 etc. cn minus 1 cn minus 1 yn minus 1 is equal to is identically is equal to 0. So is identically equal to 0. Now what does that mean? That means okay, let us go back the other way. And the set of solutions, n solutions, one given by x1, xn, where xi equal to eta yi for I equal to and xn equal to eta form a linearly Now what you do is this, okay. So you have to prove that c1 x1 plus c2 x2 plus etc. cn xn equal to 0 is identically equal to 0 implies c1 equal to 0, c2 equal to 0 etc. cn equal to 0. This equal to 0. How do you prove that? Now this means we rewrite in terms of that. Therefore, eta times C1 Y1 Cn minus 1 n minus 1 plus Cn equal to 0 is identically equal to 0. That means we have to show that y1, y2, yn minus 1 is identically equal to 0. That is eta not equal to 0. Now you see that this is a linearly independent set. So we first observe that but we already know that C1 okay, this gives rise to what is that? Equal to 0. This is identically equal to 0. Now you differentiate. Differentiating T, we have identically equal to 0 because this is a constant, so that goes off. Since independent, we have equal to 0. Now this in turn implies you want to call this I1 from 5 Cn is equal to 0. So that completes it. So that proves that they are linearly independent. Now what you can do is, see, you can reduce by one step. Thus we have order of the equation constant. Solving equation. That's the reduction that we have. Okay. If K and solutions are minus K. By successively applying the method. Of course, so this is the technique, and one can show that it is always possible to find some interval on which this can be. Okay, let us now work on this idea and see what you get. So we'll look at one example. Equation t square x double prime minus plus tx prime minus find the general solution. So essentially we have to find a solution which is independent of x1 equal to t. So for any interval we can apply the method. We shall apply the so what do you do? So your eta t is therefore we write yt equal to or xt equal to and substituting what you get x derivative of t, then and x second derivative ty second derivative of t which is equal to t y second derivative of t plus 2y substituting you have to compute the q's. P's are known, therefore q's we have to compute. What are the q's? Okay. Substituting, what do we get? What is the equation this is? So t square into y to y derivative into what do you get? X derivative is y plus ty derivative plus or minus ty. This is the equation. Therefore, that leads to 2t square y derivative and t square y derivative. Therefore, that will give you and then you have ty minus ty. So consequently, see on t is not true. Therefore, we can take it out. Therefore, this implies now put so you get z derivative equal to I think some mistake. Yes. Z by t, or we will just consider a solution of the type then you see that t into t to the power plus 3 e to the power n equal to 0. Therefore, m is equal to m plus minus 3. Therefore, one gets and then what is the corresponding solution? We have to integrate this. Integrate this. This is equal to, therefore, yt equal to e to the power minus 2 divided by minus 2. What is the corresponding solution xt? So xt equal to minus since it's homogeneous, it doesn't matter the constants. Therefore, the linearly independent are t and 1 by. So that is how you work this out. It's just an example. It's quite easy to solve it even otherwise. Okay, so that completes that part, reduction of order. Now we look at the method of variation of parameters. So the next problem that we take up is the method of variation of parameters. We just write it down. See, method of variation of parameters is used to find out okay, this method is used to solve to find a particular integral of the inhomogeneous linear differential equation. Once a fundamental set of solutions are known. This is the method to construct a particular solution of the inhomogeneous, the non-homogeneous equation equal to 0 once a fundamental set of the homogeneous equation is known. Now we know that the Suppose are two solutions of the equation 1. Let us assume or let me just write down explicitly what this is. And the given equation is a given non-homogeneous equation. For some interval t belonging to AB. Let assume Pi's and Q are continuous. Then now if x1 are two solutions of zero on then x1 minus x2 is a solution of the homogeneous equation This implies the general solution of zero on is given by A plus a particular solution of field. That is because if you take from here, you know that x1t is essentially xt plus x2t. Therefore, the difference between x1 and x2 is only a solution of the, is always a solution of the homogeneous equation. Therefore, if you want to get a general solution of Lx equal to 0, then it's a linear combination of a fundamental set of solutions of Lx equal to 0. So, you know, this is an nth order inhomogeneous equation. So, the solution of the inhomogeneous equation, the general solution of inhomogeneous equation is then given by a solution of the a general solution of the homogeneous equation plus a particular integral or a particular solution of the inhomogeneous equation. Okay, so that is what we have obtained. Therefore, okay, so assume you know the fundamental set of solutions of the homogeneous equation consists of n linearly independent solutions. Is a fundamental set of solution of the homogeneous equation Lx equal to 0. Now what we assume is that you know that a general solution of every solution of Lx equal to 0 can be obtained as a linear combination of this. So we know that every solution Excel, because we have already done the theory corresponding to that, so that is clear. Therefore, suppose for arbitrary constants C1, C2, etc. Cn is a solution of, is a general solution of the homogeneous equation. So now what we do is we assume that a particular solution, assume a particular solution of is of the form is C1T Now, what we are doing is the following. If we were to have C1, C2, etc., Cn as constants, then this would have been a solution of the homogeneous equation. Therefore, it's our, sort of trial, a sort of trial that you are making, that we assume that there is such a solution, and you are successful provided you can determine these functions. Is it possible to determine such? CNT. This is the question that you are asking. Let us see how this can be done. This is the essential problem that we have to get a particular solution. So once you get a particular solution, and if a fundamental set of solutions are known, from that you can construct a particular solution, then you have a general solution of the inhomogeneous equation. So how do you do that? Let us start working on this. Okay. Assume C1 R Okay. Now what do you have? Yt, y derivative of t, this is equal to sigma I equal to 1 to n Cit Okay, so I say C1, C2, etc., Cn are in our hands. We can choose it the way in which we like it. So now set. This is the first equation. Then what happens? Then y derivative is simply this part. Now compute y second derivative. Y second derivative of t is then equal to Once again set this is equal to 0. This is second equation that we get. Okay. That reduces to simply this part will become 0, and therefore y second derivative is this. Continue the process. Setting see, we have all these equations now, sort of. Let me write down the equation. Equations are for j equal to now compute. So you got n minus 1 equations already, but we have functions c1, c2, etc. n functions to be determined. So still there are less number of equations than the number of unknowns. Now once you have this restriction, then you see that y nth derivative t, this is equal to sigma substitute y in the equation then we have what is the final equation that you get? identically equal to sigma Lxi plus zero. But this is which implies sigma now this is the nth equation that you have. Okay. Therefore, we have now n linear equations to determine the unknowns see we are just one step short of the solution, because what we eventually determine is the derivatives of the C1, C2, etc. Cn, from which by integration we can determine C1, C2, etc. Cn. Okay. So that's the idea. So the question is it possible? This is the question. So what are the equations? Let us write down. So the equations can be rewritten in the form of transparency. These equations in the matrix form the column vector in this case. Okay. Now what happens? Is it possible to solve it? This equation has a unique solution. If the matrix C that's the condition. That means this particular matrix is invertible. Okay, so this is an n by n matrix. Okay, but that is true because and this is a set of fundamental solutions, fundamental set of solutions. Which forms a basis for the solution space. Therefore, this is not equal to 0. And this determinant is equal to the Wronskian of T. And this, you know, that these are linearly independent solutions. This is not equal to 0 for every T. Therefore, you get C1, C2, etc. C1 derivative, C2 derivative, etc. Cn derivative uniquely determined. In terms of excise, its derivatives, up to the order n minus 1 and Q. Okay. Now by integration, integral a to t or t naught t this is quite simple. I mean, it depends on how good or how bad these functions are, but by quadrature one can determine the CIs and then use the CIs. Now I want to make a remark. The remark is this. See, when you integrate this, you get an arbitrary constant. See that here it will come up as CIT plus CIT naught, and depending on what T naught is, that constants will differ. But that doesn't make any difference, because once it goes into the formation of the particular integral, so you will get a part which is a linear combination of x1, x2, etc., xn with coefficients CIT naught plus a particular integral. So that's always again a solution. So it doesn't matter. So you get a general solution anyway. Okay. CIs up to a constant. Particular integral of the inhomogeneous equation as so I said up to a constant, because those constants can be absorbed always in the general solution for the homogeneous equation. So this is how one works. Now we'll look at an example to get a feel for the problem. Let us look at the previous example that we have looked at. What is that? The non-homogeneous equation let me write it. On an interval which does not contain zero. Now that is because you know that the leading coefficient is t square and it vanishes, and that would become what is called a singular point for this differential equation. If you transform it into a system, see if you rewrite it in the form dx by dt of fx t, then you see that the terms would contain 1 by t or even powers of that. Okay, 1 by t and 1 by t square, which will just make it difficult for f capital F to satisfy the conditions of the existence and uniqueness theorem. Okay, therefore that's why we are assuming that which does not contain t equal to 0. Everywhere else everything is fine. Okay, you get nice continuous functions here. So you just do it and then get a feeling for this. Okay, that's why the zeros of the leading coefficient in these kind of equations always give a point of trouble. Okay, and the vicinity of that, the existence and uniqueness theorem won't be valid. That's the problem. That's a remark I wanted to make. Now let us work this problem. So we have seen that independent of the homogeneous equation. Of the homogeneous problem, what is it? Equal to 0. You can quickly make a check, because that you can easily get by looking at this. Assume a solution of the form t to the power m. Then what you get? You get t to the power m therefore you get m square equal to 0. This gives because we are assuming again t not equal to 0. Then what do you get? You get m is equal to, that is t and 1 by t are the corresponding solutions. Therefore, what we assume is that yt equal to c1t plus then you find out derivatives of that. Derivatives of that will give you plus c to t now set zero. It's the first equation. Okay. Now what about this is equal to this term plus this term will go and you are left with this. To our minus 2, you differentiate that. Minus 2 to the power minus 2 minus 1. So, okay, therefore, substitute it in this original equation. So, multiply by t square. So, you get t. That is the first term. The second term is plus t into x derivative. So x derivative would be this term. So c1 derivative, no, that is gone. So c1 t minus by t. Then the last term is minus c1 t minus c2 t into 1 by t. So what do you get? 2c2t 1 by t and minus c2t 1 by t. So you get c2t into 1 by t. So this plus this will be 0. Then c1t minus c1t is 0. Therefore, that implies t square c1 derivative of t. This must be equal to What is it? What is the equation? QT. So this is the second equation. Okay. Now solve these two equations. And then find a solution of this. So you get C1 derivative and C2 derivative solved from these two equations. You get t times C1 derivative t or t square times C1 derivative of t plus C1 derivative of t is equal to 0. Okay. So substituting that and then solve this equation. We have to solve it now. It is right. So what are the equations? The equations are just two equations. One, of course, solve it. When you solve it, you get 2t square therefore C1 derivative of t similarly, so you substitute that there. For C1 derivative of t, you substitute qt divided by 2t square. Okay, so what do you get? Okay, C1 derivative of t, you substitute qt divided by 2t square, then you get 1 by 2. Okay. So C2 derivative of t, this is equal to C2 1 by 2. You are substituting there. Now you see C1 derivative of t, you are substituting, so you get qt divided by 2. C2 derivative of t is equal to qt divided by 2. So you get these two, C1 derivative and C2 derivative. Integrate. Substitute and you get the general solution. Equal to into what were the solutions? C1T plus so that gives the particular solution. I hope the computation is right. You do it independently and verify. Okay, thank you very much. Stop. The next lecture we will be taking up what is called the Green's function.